Okay, last video that we're going to do on the U substitution. I started out calling it integration by substitution method because I think that's what your book calls it. That's what a lot of books call it. But usually, after you do it for a while, everyone falls into the habit of just calling it U sub. Okay, so if anybody refers to U sub, they're referring to this method, the method by which we use substitution, usually using U. And to stand for some expression in terms of the independent variable to clean it up such that we can actually move forward. Okay? Now, let's do a particularly nasty one. How about that? And right now, you're about to cry. And that's okay. Here's what we need to do. We need to look at all the different candidates and try and figure out exactly what's the best one to do. Okay? Now, you do see the fact that there's a radical. So you could designate U as the radicand. Okay? But if you do that, then that winds up being U to the 1/2. And this winds up being U. And then you wind up having just a little bit of a problem in terms of basically you wind up with fractional exponents when you really don't have to deal with fractional exponents. And I'll show you how. What we're going to do, remember I said most of the time it's the radicand, but sometimes it's the radical. Okay? So that means that U squared is equal to x plus 1. Now you're thinking, well, how do I get the differential? I'm so glad you asked. Can I differentiate this implicitly? Sure I can. Let's differentiate it with respect to x. Okay, so you get 2u du is equal to dx. And now I know exactly what I'm going to plug in. Okay, and I know that this right here, x is equal to u squared minus 1, so negative x is 1 minus u squared. Okay? Now, I think that gives us all of our pieces, such that when I do that, and actually instead of 1 minus u squared, why don't we just leave the negative out in front instead of actually distributing it and flipping the difference, okay? So we have negative u squared minus 1. Okay, this denominator is going to be u squared minus u. The dx is going to be this whole expression right here. So let's go ahead and put 2u up there, and we can put the du right there. Now, all this requires is just a little bit of factoring and canceling. U plus 1, u minus 1, that is the difference of two squares after all. This down here just takes a GCF, okay, factorization, and there we go. Boom, 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 and all of a sudden I actually have a very, very easy integral, okay? And so I have negative 2 times 1/2 u squared plus u plus c. And of course you can distribute the negative 2, but you get the idea, okay? Remember, the whole purpose of U sub is not to make things more complicated. The whole purpose of the U sub is actually to make it easier. And notice how much easier that is than that. Now, if you had actually tried to go down the road of using U is equal to that radicand right there, I'm not actually sure whether you would have gotten the right answer. It certainly would have been a whole lot more cumbersome. But basically, this is just an example to show you that sometimes there is an exception to that rule of setting u equal to the radicand. Okay? All right, let's do t times the cube root of t minus 4. Now here's one of the problems with cube root. If this t, like in the whole typeset, when it's actually made by an equation editor and typed out on your test, sometimes it's hard to tell whether that 3 belongs in that little nook right there and belongs to the radical, making it a cube root, or whether it belongs to the t, making it t cubed. And if you ever have any doubt, I would just ask your teacher, or just work it both ways or something like that, okay? I would say, is that a cube root? Does the 3 belong to the root, making it a cube root, or does the 3 belong to the t? Now notice that I put a space in there, but I'm writing it by hand. If you actually look at it in a typeface, some typefaces, it winds up being a little bit ambiguous. Now let's go ahead and go back to our default. Let's see whether t minus 4, being the radicand, is a good way to go about basically identifying u. And you have u plus 4 is equal to t. There's the back substitution right there that's going to be required for that sort of miscellaneous t floating around right there inside the integrand. And I think that's basically all it's really going to require of us right here. And so I'm going to do u plus 4, u to the 1/3 du, and then of course we can distribute it. It becomes u to the 4/3 plus u to the 1/3 du. And of course I basically put this one in just because we've been dealing with square roots the entire time. You know, I just wanted to basically reinforce the fact that you can really do it with any fractional exponent. And of course, when I add 1 to this, it's going to be 7/3. So the coefficient is going to be 3/7 u to the 7/3. That's going to be 4/3. So it's going to be 3/4 u to the 4/3 plus c. But you can't forget to substitute back in. It needs to be back in terms of the original variable. And ta-da. Okay, well, we've done enough of these, I think. Let's go ahead, like we did in the last video, and do a few examples of the definite integral, because I want to make sure that we have a couple more examples of that under our belt before we move on. This one goes from 1 to 9 of 1 over root x, 1 plus root x squared dx. Now my default instinct is going to be to make whatever's inside of that parenthesis equal to u. So let's go ahead and do that. And let's see what happens when I differentiate. Okay, or 1 over 2 root x. Now the reason why I wrote it right like that is to make sense out of why this thing looks out of place. It looks out of place right now because it kind of is, okay? If I were to go ahead and rewrite that as 1 over root x dx, 1 plus root x squared, it would look a little bit easier and you wouldn't have had such a hard time in terms of glancing at it. So just remember that any factor, especially a monomial factor when it's one among several in the denominator, can be popped up like this into the numerator because it just may be part of your du, okay? Now notice that I haven't even plugged in for that yet. Now I know I need a 2 right here, but putting a 2 right here is dividing by 2, and so I need to multiply by 2, and I think that winds up being it. So I have 2 integral u to the negative 2 du. But again, I cannot take 1 and 9 with me. 1 and 9 are limits of integration for the variable x. I need to go ahead and change those into u. So when x is 1, meaning plug 1 in for x, what is u? U is 2. Okay. When x is 9, square root of 9 is 3, plus 1 is 4, u is 4. Okay. And now when I integrate, I don't really have to deal with anything else. Okay. I wind up getting negative 1 over u, or negative u to the negative 1. That is evaluated from 2 to 4. So I have negative, let's go ahead and put that in brackets. Go ahead and plug in negative 1/4 minus negative 1/2. Okay, boom, boom. And that winds up being 2 times 1/4, or 1/2. Okay. And you just have to get used to every time you change it from x to u, change the limits of integration. And of course, the very process of using the u will have cleaned up that integrand significantly, or it should have. If it hasn't, you've done something terribly wrong. Okay? And we get to here. This right here is a very easy integral. We integrate it, we evaluate the difference, and give our answer. Okay. How about 1 to 2 x minus 1 root 2 minus x dx? Okay, well I've seen one of these. It's a back substitution one. But I haven't done a back substitution one that's a definite integral. Now, does that really matter? Absolutely not. And I know that x is equal to 2 minus u, so x minus 1 is going to be equal to 1 minus u. Okay? And I know that, basically, if I differentiate both sides to get the differential, that's going to be du is equal to negative dx, or negative du is equal to dx. Okay, there I have all of the stuff that I'm going to use. Now, let's go ahead and plug it in. Now, x minus 1 is 1 minus u. And of course, when I substitute in a u for that radicand right there, it winds up being u to the 1/2. That is a negative du. Now, I have two choices. I can either put the negative out in front when I put that here, or I can use the negative to flip that difference back into descending order. And that's what I'm going to do, okay? Because remember, when you multiply a difference by a negative, it just flips it, okay? Now, from here, it winds up, of course, once I've gotten it into the u form, it should be very, very easy. It's just undoing the power rule, and therefore I have 2/5 u to the 5/2 minus 2/3 u to the 3/2. Now remember, I have forgotten to actually bring my limits of integration along for the ride. So let's go ahead and do that. I know that when I plug in 1 for x, I'm going to get 2 minus 1, or 1. When I plug in 2 for x, I'm going to get 2 minus 2, or 0. So that's 1 to 0, okay? Which means if I'm going to actually, I can actually evaluate it like this. It winds up, basically flipping the difference, winds up being the same thing. Let's go ahead and just do it the way we're used to doing it. So I know that going 0 to 1 is going to give me u to the 1/2 minus u to the 3/2 du. Again, instead of putting the negative out in front, I am using it to flip the difference. And so I know that that's going to be 2/3 u to the 3/2 minus 2/5 u to the 5/2 from 0 to 1. And when you're plugging in 1 and 0 into polynomial terms, it winds up being very easy. So that's 2/3 minus 2/5 minus 0 minus 0. Okay, and you get a common denominator of 15. This is going to be 10/15. This is going to be 6/15. So the answer, the difference between them, is 4/15. And that winds up being your answer. I think that should be about it. I've done a smattering of all sorts of them in the 6 videos that I provided for you. If you have any questions, please do shoot me an email. I'll be more than happy to supplement what I've done here. But I think I've given you a pretty good broad base sampling of the types of problems that you're likely to run into when you start doing substitution problems. As always, if you have any questions, please do email me, or tell me when we meet online. Bye.